Okay. Hello, everyone. I'm Sereina. And I thought I'd talk today about the 10-year anniversary we have of the Conformer generator that hopefully all of you use when you use the RDKit for that. So I thought to kick this off, because we have basically a Conformer generator session now, I want to give you a brief history and maybe also an explanation of some of the flags that if you use the Conformer generator in the next time, you actually maybe know a bit better why you're choosing certain things or not. But before I start, I want to acknowledge the people working with me on this. So you see, I think you see the mouse, right? Yes. So of course, Greg and I started that. Actually, we had it first published in 2015, but we started it already earlier in 2014. And then Jagna and Zhuzhe, they worked with me on the macrocyclic and small ring torsions of ETKDG. And then who you see afterwards, Niels and Jessica, they're working now with us on this, with the new improvements. And just as a short plug, Jessica is finishing December, and she's a good cheminformatician. So if you're looking for one and a good programmer, then please talk to her. Okay, so where does this started? So maybe first, what is the acronym? And you can be thankful for Greg that it's only ETKDG and not ETKTDG, which it was originally. So we dropped the terms, the T for the terms. I'm not good in naming packages. I think Greg is not necessarily good in naming. So that's why we ended up with an acronym that no one really can pronounce, but you still remember it because you struggle with pronouncing it. So ETKDG. ET stands for the experimental torsions. And that was the main idea, was bringing into distance geometry the information about torsional preferences that we get from so the crystal structure data, in this particular case from the CSD. We use fitted torsion potentials. So we use basically what we have in molecular dynamics force fields, which is a cosine series with up to a multiplicity of 6. And in order to basically say what are even the torsions we look at, we made use of Matthias Rare's group work. They published already 2 versions. There's actually now a layest version that eventually will also make it into ETKDG. They published these smarts patterns that have torsional, or smarts pattern for torsions, basically. So the original ETKDG used the first version here, this 2013 paper. Version 2, which was default for some time, uses the one from 2016. And this is still, and I will show it at the last slide again, the version 2 for the acyclic bonds, because this is important. The Rare group only looked at acyclic bonds. This is still the version 2 is what is in the default. Even if it's ETKDG version 3, it's still the version 2 for the acyclic bonds. And the K comes from the knowledge terms. Knowledge because we basically impose something that we think molecules should do, which is aromatic rings, at least when you look at them, should be flat. Of course, in quantum mechanics, they're not flat, but for viewing them, they're flat. So we have sp2 hybridized atoms are flat. We have additional torsion term that is just for the aromatic rings to also keep them flat. And we have straight triple bonds. And so these are just that's why we call them knowledge, because there's not really any necessarily experimental data behind there, but it's just what we expect molecules to look like. So where does this come in? This is just brief, also to introduce basically what Niels is going to talk about. Where does this come in the distance geometry workflow? So the smarts patterns are here. We basically do a substructure search. And then what is important, we first generate a normal distance geometry conformer that actually is then minimized again using the experimental torsions and the knowledge terms. So this is kind of a second optimization, and Niels will talk about that as a potential way of also speeding things up. Version 3, that's the default, what is actually there in principle. So we were thinking about what to do with the cyclic bonds because the original patterns didn't include them. So we have now 2 additional sets of smarts patterns. One is for small rings, where the idea is, for example, this is what you find in terms of 6-membered rings. You can clearly see here all your nice chair conformations are at -60 or 60 degrees. If we had the original ETKDG, we basically didn't have the right balance. And then with the additional ones, we got that better. In terms of if you look at RMSD, so this is the best ring RMSD. So if you generate 100 conformers, which of those has the best RMSD you find among these 100 to the crystal conformation, just based on the ring, we don't have a huge improvement. That's also why these are not turned on in the default. I will mention that again. What is turned on are the macrocycle preferences, because one of the things is macrocycles, once they get big enough, their bonds are actually behaving like acyclic bonds, but because they're considered to be in a ring, all the nice smarts patterns from the Rare group didn't apply to those. So basically what we did is we took this, this is moving. Why is it moving? So we took those, we just adapted them to also adhere to macrocyclic bonds. So it's the same one as the acyclic ones. And we also had to do some changes to the 1,4 bounds. And what you see then here on the right is that you get overall an improvement in the best ring RMSD. So just to close this off, so this is what you have. The first one is the default. So whenever you just call embed molecule, that is basically what you get. So that's ETKDG version 3, which means your knowledge terms are turned on. Your acyclic bonds have version 2 of the Rare patterns. So this is this ET version here. And the macrocyclic torsions are also turned on, but not the small ring torsions. You can get the small ring torsions if you only want them to turn on. This is this shortcut that has the small rings on, but the macrocycles off. You can, of course, always adjust that, but these are the shortcuts. If you want version 2, there is a shortcut for that. So that is without all the macrocyclic or ring stuff. You can go back to the original version 1. And I want to make a plug for that one, KDG, which is just applying the K terms, is actually, if you anyway plan for minimization of the conformers afterwards, you can be faster by just doing KDG. Because the ET terms, the idea of this is that you get directly a conformer you can work with, right? Using the experimental torsion preferences. If you're afterwards going to do an optimization in QM, with QM in the gas phase, this has nothing to do, and Jessica will talk about this. This doesn't necessarily have the same preferences as the experimental crystal structures. So if you anyway are going to do that, you can save yourself the work or the computed the work of applying the ET terms and just do KDG. So keep that in mind. If there is a optimization afterwards, that's actually simply faster. Okay, thanks.
We have a clicker. What the hell is this? This is Acrobat. Yeah. Oh my God. I guess you can also go full screen here, but I wouldn't know how. I'm gonna walk around when I have this on? No. All right. This is for the room. Okay. I talk loud enough? Okay. Well, not walk around. It just doesn't work. So I obviously don't know how to use a computer. Does anybody know how to make some application show PDF? Oh, there we go. And now more actions present, maybe. Hey, that's not too bad.
Okay.
Okay.
So that should work.
Perfect.
But you need to be there.
Okay. So, welcome everyone. Good afternoon to my talk about conformer quality in ETKDG. And I would actually like to start off with saying thanks to Sereina for letting me work on this. Also, thanks to Greg for trusting me with this project. And thanks to Jessica as well. We work together on some of this, and it's very nice working with you. Now, when we talk conformer quality, what a lot of people think about is, do we get conformers in our ensemble that are relevant for my cause? So the question when validating is there something in my ensemble that is close to a reference where the reference can be crystal structure or bioactive compounds? This is one thing people think about. And then the second one is, how much does it cost me in time or compute time? But what is mostly just assumed and is, validation also, there is benchmarks for the ensemble quality. You can look at RMSDs or torsion fingerprint deviations. And then for runtime performance, it's just basically using a stopwatch, right? Of course, it has to be said that there's a trade-off between speed and accuracy. But obviously, for a certain amount of accuracy, we should aim for the fastest possible implementation. Now, what is missing here, and what is assumed always, is that we have what the K terms are here for, basic conformer quality. So things that in every conformer should be there. So we should have valid bond angles, we should have valid bond length. And this is very simple things that we just assume are there, right? And then there's the K terms that make aromatic rings planar, SP centers, angles around SP centers to 180 degree. We just assume this. And in, you can only see 70% of my slides, but if there's something. Oh, okay. Oh, okay. Yeah, well, does this work? Yeah, perfect. In benchmarks, it is checked whether we have this basic conformer quality, but it's often just a side note, as in, oh, we find that sometimes bond lengths and bond angles are off, but we really focus on the torsion states. Recently, there has been a benchmark by Charlotte Dean's lab where they check AI-generated structures and purely focus on the actual conformer quality of all the single conformers. And we thought, well, since people have showed that sometimes our bond lengths and bond angles are off, it might be a good idea to also screen the conformers we get from ETKDG with like an orthogonal approach and not looking at RMSDs and TFDs for torsion states, but at the things that we just assume are there. Now, before we go into what I'm doing, we need to ask the questions, where can we improve and what can we actually expect from the conformer generator? And this is getting a bit technical, sadly, but we need to go through this together. This is, again, the DG algorithm schematically. What we can change is, for bond lengths and bond angles, we use a force field to estimate 1,2 and 1,3 distances. We can change that force field to improve this. We can also change, we will not exchange the algorithm because it's been there and we want to make small changes. We can change heuristics that we use in building the bounce matrix. We can improve the initial embedding. We can have a look at the K terms that are here for conformer quality. And we can also look at the coordinate refinement process that is actually just a minimization. What's not in this picture on the left from the publication is that there is also a bunch of checks at the end of our workflow that are looking for things that we know sometimes go south, okay? But the problem with, if we pass, we get a molecule, a conformer. But the problem with this is, if we just add more and more checks, this is the most expensive solution to our problem, because this happens at the end of the algorithm. And if we did all the work of embedding a conformer and we find that it's not good, we did all of the work for nothing, and we just discard this try and we start over again, basically. So we would actually want to start at the top and not just add checks in the end. Now, what can we actually expect? So for my test set, I have the platinum data set, that is PDB structures. I have a selection of COD structures, making sure that we cover as many torsion patterns as possible. And I have a set of benchmarks that I just check for that we think every conformer should pass. So we look for steric clashes. We look for things that we are directly enforcing with the KDG terms, just to make sure that they actually yield what we think they do. And what I can do now is I can look through crystal structures with my checks and see what are the valid ranges of values that I would expect, and then flag conformers easily that are outside of these ranges of values that I see in crystal structure. Now, I first started applying these checks to normal DG ensemble, so no ET terms, no K terms. And the first disturbing thing I find is that very rarely, but sometimes we find clashing atoms. And this is something very unphysical and obviously something that we cannot accept in a conformer generator. Now, what I'm doing to fix this is what I told you not to do, and this is adding a check. But since this is happening only so rarely, it makes much more sense to just discard these few tries than to change the algorithm in a big way to prevent this from happening. Second thing we found is that there is no K term for allene and cumulene-like structures. So we were just checking for triple bonds, but other SP centers, like in a cumulene, we didn't apply a K term to keep this linear. Additionally, there was a term in the final checks that would always discard allenes that were actually linear. So applying our benchmarks, my test run, we could easily fix this, and this is now already in the public, so in the releases. So this was really low-hanging fruit. But now for bond length and bond angles, it gets a bit more difficult, because in theory, this is something that we should know very well, right? This is well defined, or we have sources that well define bond lengths and bond angles. We are using the UFF for estimating 1,2 and 1,3 distances, and the UFF is very coarse-grained. It's very robust because we can throw almost anything at it, but it's very coarse-grained. And we thought, well, can we exchange by using the MMFF, and that is a bit more fine-grained, and see if we get better bond lengths? This is again for a DG ensemble, and what we see is that we can actually improve the bond length by some extent. Turning on the ET and K, so this is on the top, so this would be actually a very nice solution to our problem. Turning on the ET and K terms, however, we see that we lose a lot of the accuracy that we gained by replacing the force field. So our bond lengths get worse again when turning on the ET and K terms. So I did a lot of investigation where this is coming from. But in the end, what we care about is that our distances in our molecules are inside of the bounce matrix that we set in the beginning. Now, looking at how many distances are inside of the bounce matrix, and beware, there's a typo, it should be 0.01 angstrom and not 0.1 angstrom. I'm sorry for that. If you look at the different methods that we have for DG, you can say we're still reasonably inside of our bounds. But then for ETDG and KDG, we find that we sometimes have 15 or 16% of our bonds that are outside of the bounce matrix. And the bounce matrix is what we define with some padding as the possible conformer space. So we know, or we see, that a lot of the conformers we create are actually not inside the space that we define as possible, right? So this is a big problem. And what we need to do first is make sure that the algorithm produces something that it should produce before we fine-tune the input, because we can exchange the force field all we want. If it's not obeying the force field, there's no point, right? So I thought, well, maybe we cannot go to force field, maybe we can just look at the coordinate refinement process and optimize the optimization, basically. And the idea was first to just tune the relative weights in my minimization and start with DG and then add the K terms, ET terms, and so on and so forth, just to see if you're just using a wrong relative weighting of the force field. Now, first try, I played a little bit around with the force constants, and if you see default is master RDKit, default new is master RDKit with new force constants. We can actually reduce our bounce matrix violations quite a bit. However, Greg asked people for who is RDKit too slow, and runtime increases dramatically, and this is not something you want to pain you with. So I tried a lot of different things. There's a lot of parameters, and I either made it slower or worse. So, and before turning completely bald, I thought, well, I need to do something else because just turning knobs here and there is not going anywhere. So I asked myself, where do we actually spend time? And for a DG conformer, a chiral DG conformer, here you see steps that we spend in the minimization. We actually have two sequential minimizations. We have we create a force field, minimize for, in this case, 300 steps, create a second force field, and then minimize for 10 steps. You might ask yourself, is it really worth it to create the second force field just for these 10 steps? If you do ETKDG, there's actually 3 sequential minimizations now that are going on. And I'm asking myself, might we save some time if we just combine all of this into one and do everything in parallel instead of sequentially? That's the basic idea. For non-chiral molecules, that is very simple because they're always in 3D. I can just put all the terms together. However, for chiral molecules, the way the distance geometry algorithm works, we need a 4th spatial dimension. And this is where it gets tricky because I cannot show you, and it's also hard to imagine because you just can't, right? And the problem is also that for the ET and K terms, we have dihedral angles. And the dihedral angles are not unambiguously defined in 4 dimensions because we need the cross product, and this itself is not defined in 4 spatial dimensions. So I found math done by Crippen saying that we can get the cosine of a dihedral angle, and we use the cosine series for our ET terms, but we try to go away from the cosine series. You will hear more about that from Jessica. So this is not the option. Looking at another old paper, now from the Van Gunsten group, they did 4D molecular dynamics. So molecular dynamics in 4 spatial dimensions, and they found that they would just use the 3D projection for calculating the torsion, the dihedral angles, and also the gradients then in turn. So I thought, well, maybe I can try this and just put together in 4D what I need, and the things I cannot calculate in 4D, just take the 3D projection of that and calculate forces and energies like that. Now for DG and non-chiral molecules, that works. And it's not surprisingly because it's the same force field. We go from a 3D force field to a 3D force field, nothing really changes. If you go to chiral molecules, we go from 2 force fields to having 1 force field. And what we can see here, so now blue is master implementation, yellow is master implementation with new force constants, and orange is the new implementation with the new force constants. And what we can see is that we can reduce the violations in bounce matrix things and also reduce the time. Because first of all, we only create 1 force field, and also we spend less time in the minimizer itself. So that's very great. Now, this is just DG. What if you add actual complex terms that are the K or the ET terms? For KDG, so now the chemical intuition terms are added, I can actually see the same trends. So I can drastically reduce my bounce matrix violations with the new implementation, and I can also save some runtime, which is actually very great. Same goes for ETDG. However, here the reduction in bounce matrix violations is not as prominent as we see in KDG. But still, we can reduce them, and we also don't spend more time minimizing. For ETKDG, we can reduce them, but we spend roughly the same amount of time. This is due to the fact that we sometimes have conflicting K and ET terms. We have the K terms trying to keep centers flat. And if these centers are part of an ET term that has a maximum at 0, it can be that we have contradicting forces. And this makes us spend a long time in the minimizer. And yeah, this is why we cannot get. But overall, I think this is very nice because we can, at least the algorithm, we can force the algorithm to do a bit more what we think it should do and also not spend more time. Well, we now covered the quality and the timing, and you might ask yourself, well, are we actually now losing in the ensemble, right? Are we now generating less diverse structures or not? For ETKDG, if I look at the RMSDs or the TFDs, so y-axis is the new implementation, x-axis is the master implementation, I can see that there is no trend either towards the worse or the better. So I assume that the quality of my ensemble stays the same, while the quality of my single conformers increase with equal runtime. This is all great, but we also face some problems. As I said before, the conflicting ET and K terms are really a problem because we now spend a long time in the minimizer with fighting terms that we should get rid of. And the other problem is that it works for most of the cases. There's still roughly 0.5% for KDG of very strained fused aromatic systems or macrocycles, where I still flag unphysical conformers, and I need to investigate why these 0.5% are still not behaving the way we want them to behave. Another interesting thing is that I found for, now this is again pure DG, so no preference for any torsions. If I get better in the bounce matrix, my TFDs get worse for some molecules, for most not, but for some. And I'm not sure yet whether this is a problem with the torsion fingerprints or whether our 1,4 distances in the bounce matrix are actually off, and now that we're obeying them, we get worse conformers. This is something I need to still investigate. Now the big question, when will this hit the public? This is going to be breaking changes, and the idea for this is to replace the existing algorithm. And since it's breaking changes, it needs to go in a major release. Now, for it to go in a release anyway, it needs at least to be as robust as the current implementation. Because the current implementation, even though not perfect, it's very robust. And as long as I still have problems that I don't have with the current implementation, it will not go in there. So talking major releases, I hoped to get it done by the fall release. It didn't turn out that way, so hopefully, I will not promise, but hopefully we'll have it out in the March release, in the big March release. And now for a little conclusion, using an orthogonal benchmarking approach, we found some very simple fixes that we can apply that save us clashes and add K-terms for the allenes and cumulines. Replacing the force field for the bond lengths and bond angles works, but we find that the algorithm is not obeying our input all the time. As a possible solution to this, we propose this new implementation of a parallel minimization instead of sequential ones that could improve the things that we found out are not going well without spending more runtime. And as soon as all of this is done, we can then focus again on the ensemble quality and go to the next torsion version library and look at new fits on how we can fit the torsion patterns even better. And with that, I would like to thank you very much and give the word to Jessica. Thank you.
Right on time.
Right on time? Perfect. Happy to take the questions after Jessica's talk or in any of the
Did I not get the speaker view?
What's that?
Did I not get the speaker view?
No, you can't get the speaker because that's being shared by Zoom.
Ah,
So
okay,
you
fair.
can use that to advance.
Okay.
You should stand more or less here so that the room hears you, but you're not
Okay.
as loud as I am.
And is someone on Zoom? Is this actually being shared properly on Zoom? Okay.
And we'll, the 3 minutes, we'll make, my phone will make the noise.
Okay. Yeah, thank you everyone that came before me in this section now for the introduction. I really went for a title that rolls off the tongue. I'm going to talk about the ET terms that were introduced, and I'm going to refer to them as the torsion motif angle distributions. First, acknowledgements for this project. Sereina and Greg are my supervisors for my PhD. Then Paul is, or was now, he actually finished already, one of my long-term collaborators. And John was a student of mine that also helped out. And then Niels, Ricardo, Shuyu, Enrico, and Carl. I talked to lots of my colleagues about my problems and projects. So how did this whole project start? It was actually in not one, multiple of our group meetings that we always have on Wednesdays, that we pull also papers and talk about papers. And often comparisons are done between ensembles that originate from different sources. So some of them, for example, from a conformer generator, which in the case of ETKDG is biased towards crystal. And then you have something like global search algorithms, more in the recently like GOAT, that is really tuned towards gas phase or originating from QN data. And when we then compare the results that you get from the two, or the global minimum that you found in the ensemble you look at, you maybe shouldn't be surprised that they are not comparable or they don't give you the same result. Which then led me a bit to the question with the, okay, what are we actually comparing? I do understand if I look at a molecule itself and one is in gas phase and one is in a solvent, that if I would pull, for example, from a simulation, the torsion distribution of one of the dihedrals, and I would compare the two, that I wouldn't get the same results. But actually with these torsion motifs, they're accumulations of many molecules where these smarts patterns were actually designed to somehow reflect meaningful chemical environments. So a bit more on what these torsion motifs are. They originate from the torsion library. Sereina already elaborated a bit on that. They are a hierarchical system of smarts patterns that are developed from the Rari group. Originally, the idea came from Klebe et al. And then there were 3 releases where they tried to design these smarts patterns and revise them as they were going on. But they're always sorted in, they have the bond types that you would encounter, so CC, CN, CO, and so on. And within one section, you go from most specific to most general. And then the kind of thought is that you could run a molecule through that and you would get the best fitting hit, and you would get a torsion profile that you can then relate to the molecule you're looking at. And the data that is in the torsion library is extracted from the CSD, so it's crystal data. So my experimental setup was then, okay, for these for these torsion motifs that I have in form of these smarts patterns, can I design an experiment where I get data not only for crystal, but also for vacuum, water, hexane, and any other solvent that I could possibly imagine, and then compare these exact extracted torsion motif angle distributions to each other. So I started out by selecting the CSD as my data set to work off. I have my crystal extractions already. And then my colleague Paul worked very nicely on this GNN-based implicit solvent that is using a delta machine learning scheme as well, where you can actually run conformational ensemble through this scheme and you get rapid access to the conformational ensemble in different solvents. The current version that's published in JAX allows you to go, I think, for 39 different solvents. But the ones that I'm now going to talk about or that I selected are the comparisons between crystal, vacuum, water, and hexane. And as a kind of add-on to this as well, I did not only do it for the CSD, I also did it for the DASH dataset, which is comparable in size data set to the CSD, but then obviously for those I don't have crystal data, but I could do some comparisons, for example, to the vacuum profiles, just to see when I compare the results then for the extractions that I've done, are they data set dependent in any shape or form? Yeah, And then maybe also that's important going forward. When you actually do these minimizations, you get these, in my case, 100 conformers per molecule that you ran. And with that, because you run the OpenFF force field and the gneiss minimization together, it's so the force field contribution and then the gneiss contribution. So what you get back are the minimized conformers in the solvent and energies that are associated with these conformers as well. And there was also another thing that's a bit implicit when you think about the cosine series that we fit. We actually assume that these profiles are symmetric. And when you think about it, it actually also makes sense that they're symmetric, because for every molecule that I find in the CSD that matches a certain torsion profile, I can construct the exact symmetrized molecule. So if I would mirror on 3 atoms that are in the dihedral, I could really construct the exact same counter case. And then I would have the mirrored angle value that technically I indirectly with that also discovered. So whenever I now extracted the torsion profiles with the exact torsion values, I did that mirroring as well. And I added with a data augmentation in that sense, then the torsion values, which just gives me cleaner profiles. And already in the profiles itself, I can see that they are symmetric, which makes fitting later on easier. Then, as I said, with all the different conformers I get back through the gneiss approach, I also have these energies associated with them. And the question was a bit, okay, am I really interested in the high energy conformers that I get back from them? Because if I include or not include them actually has an influence on the overall shape. And yes, maybe the best approach would be to Boltzmann weight them, but because the energies that I get back here are actually missing the entropic contribution, I had to come up with a threshold for the energy, which ones I would include. And going forward, we went with the 25 kilojoule within the lowest energy one that I could find. Then also, this is an overview of all the comparisons that I can now do, because for every single torsion motif, I can compare these 4 different environments to each other, but there are actually 2 different groups of comparisons that are in there. So one is comparisons between the computational workflow and the crystal, where there you also have this force field contribution. So you could always argue against any differences I see and say, oh, is this just because of the force field that I selected? But any differences I see within only the computational workflow itself, there can say the differences that I see are not coming from the force field, but from something that gneiss modeled, or which is then hopefully coming from the solvent. But even the comparison of the torsion profiles is not trivial, as I found out, because in literature, if you look at anything that has been done in the field, it's mostly case-based and expert-driven, which translated means you look at them by hand. And if you talk about over 350 different comparisons and then 4 in each category, that's just a lot. So I had to come up with a system that I could run automatically and that would refer to kind of the 3 main points that as I would normally look through them by hand would consider, which is shift in peak position, then changes in the peak heights, and then also peak appearances and disappearances. And I didn't really necessarily want to weigh one of them being worse than the other, but I really wanted all of them to be covered. And then also, this is an important one, I wanted it to be sensitive to global and local changes, because what you also sometimes see is that you observe splitting, for example, of a peak, which is a very local change. And then depending on the metrics that I chose, I'm going to talk about them in a second, they're sometimes not really covered that well. So there are 2 metrics that I then went with. One was the second order Wasserstein distance, which is more covering changes in mass. So I think maybe some of you are familiar with the overall concept, but Wasserstein in general is about how much mass you move how far. And the second order is just penalizing outliers a bit more. It's a bit more sensitive to that. And then chromatophoresis is more capturing shape changes, so overall shape changes. It's kind of referring to the max difference in CFDs, if you want to think about it that way. But because they're both describing differences, but they're looking slightly different at the problem, and I wanted them both to contribute equally. So what I had to do was actually normalize them to the theoretical maximum value, which I got to by constructing the most different case you can come up with, which is moving all the mass as furthest away as possible, which on a circular distribution is just moving it to the other pole, if you want to think about it that way. And then I just added them and divided them by 2. And that's how I come up with my tau metric here. So now we are going to take a look at some of the results. I'm first going to talk about more of the overall results, which is now here. I don't know how many people are used to reading CDFs, but basically my metrics both describe from 0 being they're exactly the same to 1 being the most different. So here in the CFD, if you want to then read it for the tau value, you get that vacuum and hexane are the most similar to each other because the CFD is building up the quickest to 1 for the smallest tau values. And then everything from the computational workflow, so vacuum, water, and hexane, is the most different to the crystal. And then you have the other ones, so in the computational workflow, that water and hexane and vacuum and water are somewhere in the middle. And when you think about it, the result that vacuum and hexane are most similar is actually also a nice one, because as it is the most apolar that I had in there, that's the most similar to vacuum, is something that I thought as reasonable. And because I also wanted to make sure that I can somehow trust my newly defined metric, my tau metric, I also wanted to know in the other 2 what different results only the second order Wasserstein or the Kramer-Mises would have given me, and they both would have described the same trends. There are only minimal differences. And this is now basically just showing exactly what I've showed you before in the CFDs, just in a different way of presenting it, and not on the tau metric, but on the Kramer-Mises and the Wasserstein. And here it would be the further you are in the left corner, the more similar they are to each other. So you can see again, if you get a spread out to higher values, which is the case for everything that's on the top line, that would mean that they are the most different from each other, which then kind of is the same conclusion also on this plot, that crystal is the most different to all 3 other environments, and vacuum and hexane has the smallest values. But this was now kind of looking at it on a global scale. But even though I don't like it, sometimes it's also nice to pick out examples and then try to rationalize on hand-picked examples if you can understand where these differences are coming from. And this was already a quite nice one, because you can see that the differences are quite striking. So you really have crystal as the outlier, whereas the other 3 environments really look the same. And the smarts pattern, if you can see it here up top, actually, I think it was Greg who looked at it and was like, oh yeah, I actually know this smarts pattern or this motif. It's something that I've seen before when I was actually designing molecules. So here, what is outlined with the dashed lines is everything that would be matched by the torsion motif. And then everything that's in orange, in the like fully colored in, that's the actual dihedral that you extract the values for. And then if you remember, we basically saw that in crystal, the preference is clearly at 0, whereas for everything else, you have also these values at 110, and then the counterpart, the symmetric counterpart. And if you look at it and you look at the packing that you find in the crystal, you can see that you have these intermolecular hydrogen bonds with the other copies, molecular copies you find, with the 2.4 here, which then means there is a steric hindrance of these OCH3 arm moving in. So you're really fixing it to the torsion value at 0. So looking at this, you can then understand why the torsion preference for the crystal would look so different in comparison to any other solvent or environment, as crystal is not a solvent. Then for this one, though, you could argue, that was the argument that I said before, okay, I have crystal now really being the outstanding different scenario to all other 3. So the argument could be, well, is it just based on the force field? But then if you look at an example like this, you have a case where crystal and water are actually the most alike, and vacuum and hexane are another group. So here, the differences cannot be purely explained by the force field. And you see the clear preference for vacuum and hexane would be at 180 degrees, whereas for crystal and water, you have some population being around 180 degrees, but then also more a bit offset at 0. And if we then look again at what this torsion motif actually encoded, you can see that there are 2 intermolecular hydrogen bonds that can form between 1 and 29 and 28 and 6, so between the fluorine and the hydrogen, and then the hydrogen and the oxygen, which are then making this conformation prefer to be at 180 degrees. But for the crystal packing here again, you have this interference with another molecular copy, where you then would disturb this preference at 180. And we can even also understand why there might be this slight offset as 0 degrees, because if you move up the torsion to be at 0 degrees, you have this steric hindrance, the bumping of the hydrogens 28 and 29. So we understood it for the crystal packing now, but can we also now rationalize why that would be the case in water? So what I did here is I ran explicit simulations and tried to see if I could see the hydrogen molecules, the water molecules in a position where they would interfere with the previously identified intramolecular hydrogen bonds. And there were actually 2 molecules that are always there. I looked at density maps as well, that are interfering by just forming these really stable hydrogen bonds. So we could understand as well why we see these preferences or these differences, which I thought was quite a nice result. And then on top of that, because this was now all the rationalization that there are these differences between the different environments, but also as Niels already alluded to, if we move to another version of the ETKDG, we would also want to include a new functional form, which is called the rat mirrored Gaussian. So we're replacing the former truncated Fourier series, so the cosine series, with Gaussians. And we also wrote a procedure that we can fully automated fit any new extractions that we have, which now gives us access to technically a conformer generate in different environments to be implemented. Yeah, and with that, that's the conclusions are that we do have these significant differences. Hence, we maybe shouldn't be comparing these ensembles that are originating from the different environments. Also, the trends that hexane and vacuum are more similar than hexane and water is within the chemical reasoning, and the crystal environment is really the most different to all other ones. And with that, I thank you for listening.
Okay, so we're going to do questions for all 3, if there are any. Before that, Jessica she doesn't yell and I yell. I want to make the point about comparing conformer generators that she made, just make it a little bit more loudly. If you have a new conformer generator and you want to compare it to, for example, the RDKit, if that conformer generator is to generate conformers in the gas phase, or in solution, you should not be using ETKDG, right? As Sereina said, the ET terms are for reproducing crystal structures. So by adding the ET terms to your conformer generation, you are explicitly biasing towards the condensed phase. You're biasing towards crystal structures. So if you want to compare, if you want to use the RDKit as a comparison point, you should be just doing KDG. Is that clear to everybody? That was the thing that I've been ranting about for a while. And Jessica just showed you the evidence for why you might want to do this. Hopefully it's clear to everyone. Okay, having said that, are there questions for the 3 speakers? Chagos.
Hunting down to mimic the perfect torsion distribution histogram is really the thing to do, because after all, these torsions are coupled, and if torsion 1 is minus 120, and torsion 2 is no longer allowed to sample its entire histogram. You don't know this, but at the end of the day, if you just have a simple model where you say, okay, this kind of torsion at plus 100 degrees never, no way in hell. There's some exclusion, dropout values that are never ever seen, no in water, no in hexane, no in the crystal. Because at the end of the day, what do you do with these conformers? You're using them for simulations, using them as crude, as ground truths is not really. When somebody does rigid docking with the conformer as the outsider RDKit.
So that is not true. But I'll let Jessica answer the question.
I would also, it really depends what your pipeline is and what you're going to work on. Like, obviously, if you just want it as a crude estimation, you could just use KDG, and that's what you should do. But I think there are people that are trying to get some grasp of the conformational ensemble from at least an initial guess from the conformer generator. And also, as you're saying, there are some values that will never be populated because you then have some clashes and you just know for this one molecule, it's not going to be true. I think that's what the torsion motifs are for. So you're trying to encode relevant chemical environments and you know that they are going to exhibit something that's similar to that at least. And yes, you're right, there could be still cases where there is a peak that's not populated, but I still think it gives you a fast method of estimating in a good way what it could look like. You don't agree?
Need a whole force field and then have some overall energy term that says, yes, it is an interesting conformer or not. It's very tricky to boil it down to the torsions only. If you have the right torsion with a bad valence angle, it's going to be a problem as well. Yeah, so can be sweaty.
Yeah.
I think the question for me is more, you please know that the floor is most of the piece of the metal. So, and yes, what we should do is to work on the force field, really improve it, and not to try to MMF.
No.
Yeah. Maybe repeat that question.
Okay, just to quickly repeat. So the question is, should we work on the force field or not? So very clear, there is no force field in ETKDG. So what is used for the initial bounce matrix, somewhere you have to get the bond length and bond angles from. And so that is currently taken from UFF. You can replace that with MMFF. There's no optimization. If you want to have the conformer optimized with a force field, that's you adding that.
What my question? Not optimizing the force field and make the force field optimization, it's optimizing the data in the force. Okay, the data you take as knowledge.
Yeah, so I mean, but this is I think what Niels showed, right? Is that we first have to make sure that the conformer generator really adheres to that initial input. Because with UFF, you can actually ask, is this a bug or a feature if the conformer generator is a bit more wiggly on the initial bounce matrix? In the case of the UFF, it is actually a feature because UFF is not, I mean, it's robust, but not very good. But if you, for example, put in, and you can do that, we have an implementation for that, for example, the parameters from OpenFF, then you want the conformer generator actually keep them and not having a bit of leeway in the bounce matrix. So that's why we're working on that. But in principle, and this is one of the things we're working on, is that you could then plug in any kind of source you would want to get your initial bond lengths and bond angles from, because that's basically an outside cost, right? You just get the values and then you plug in into the conformer generator.
My hope was force field data is the starting point. And maybe the force field data is better.
Then you can talk to the open force field people.
I think one additional point to that, it's clear for the bond lengths and the bond angles, we're limited by the accuracy of the force field we have, assuming that Niels's code is implemented and we're actually doing those, like obeying what we tell it to do. I think the other thing that's important to look at, and hopefully we'll get to this at some point, is the rest of the way that the bounds matrix is calculated. There are terms beyond 1, 2, and 1, 3. They're terms, they're getting a better guess of what the 1,4s in the bounds matrix should be, and in some cases the 1,5s. I mean, I think we can do a better job there, which will help with conformer generation. And I think we can do a better job in very constrained ring systems in conformer generation, where the bounds matrix at the moment we know that there's some real problems. For example, in aromatic 5-membered rings containing sulfur, to get very specific for something that's actually not all that uncommon, the conformer generator has a problem with those. And that's because the bounds matrix, we're not doing a great job of setting it up, and we could do a better job there. But I mean, I think we would all agree that if we can do a better job of setting up the bounds matrix, 1, 2, 1, 3, and all of the other terms, we'll get better conformers once Niels's work is in place and we're actually making sure that the conformers that come out obey those constraints. We have time for maybe 1 or 2 more if there are any. Yeah.
These diffusion-based conformer generators and state-of-the-art in these methods.
So the question was how I can do this one. Yeah. The question is how ETKDG or whatever in the RDKit compares to the state-of-the-art methods based upon neural networks, basically. So the problem with that is that most of those benchmarks are relying upon gas phase structure prediction. And so the people who do the benchmarking use ETKDG, which is trying to produce crystal structures, and then they compare it to gas phase structures, and it does very poorly. And the fact that it does very poorly is a feature, not a problem. The way they should do those evaluations, which they don't do, is to use KDG and then compare. And we don't have the answer to that because we've not done that validation, and neither have they. So we actually, unfortunately, do not know how it compares against those methods because people keep using ETKDG instead of KDG for this. Maybe time for one last short one before we go to coffee.
Isn't the open force field also trained on the crystal plaque structures as well? It's trained in the CSD, so it's gonna have roughly the same terms.
So being on the scientific advisory board of OpenFF, I hope I can answer that. The way I remember is that I think the bonded terms are from also, I guess, crystal structure, the 1, 2, and 1, 3. So bond angles and bond lengths, but the 1, 4 are fitted to QM profiles. So that's the torsions don't come from the experimental.
Good. I'd like to thank all